Okay, so let's talk about graphing in simple harmonic motion. So one of the things that they'll ask you to do occasionally is to make a graph, and I'm just doing this one first because it connects to our definition. Once you make a graph of force and displacement, or maybe acceleration and displacement. I mean, it's the same things, right? Just this one's going to be that one divided by m. So what should these look like? This is true for any simple harmonic oscillator, a spring, a pendulum, anything. It doesn't matter if the spring's vertical or whatever. It can be a ball in a bowl, whatever's fine. And so we know that our definition for simple harmonic motion is going to be F equals minus kx, or an acceleration equals minus k over mx. But once again, it doesn't really matter what these are. It just matters that F is proportional to negative x, and that acceleration is also proportional to negative x. So these should look like just a negative x slope graph. So just right through the origin, slope down. Doesn't really matter how tilted they are, because proportionality, that's all that you need to get. So just a straight line passing through the origin. Another one that is often very, very, very common is you'll get, I'm going to do two of these, some position versus time graphs. And I think the most common one to get is, we'll do x. I'm not going to worry about units on this graph just because we're not putting numbers to it. And this is time, this is time. So I think the most common one is going to graph, and it makes the most sense conceptually, is if we think about what will the position of a spring or a pendulum be when I use it. So but to do it, I have to take my pendulum, I have to pull it to the side, and I have to let it go. So it's going to swing back and forth. But where does it start? Oop, knocked my paper sideways. But where does it start? Well, it starts in that direction I pulled it. So let's assume it starts in the positive direction. I pulled it to the right. So it's going to start here, and then it's going to swing back towards the middle, right? So at some point it's going to pass the middle, then it's going to pass the other side, and it's going to swing back to the middle, and it's going to pass the other side again. And I could extend this farther if I wanted to. Maybe I'll extend it just a little farther, but I don't want to run into my other graph. And then once here you're back at your initial position, then of course the next thing you do is swing back to the middle. So if I connect these dots with a little bit of a creativity and insight, I mean, poorly drawn, but so is everything else I do. So we should be used to it by now. What does this look like? This is going to be cosine of some function of t, right? So I'm just going to say omega t for now. We'll get back to y. And maybe like I need some constant out front to determine the amplitude. So if I say this is a, and then I can put numbers here, but don't really care what they are. So that would tell me what this omega is. But another option is like, what if my pendulum is just hanging there instead of, pulling it? What if I somehow smacked it or shot it with a bullet or something like that? Well, then maybe it would look like start from here and then accelerate and go off to the side and then swing back, and then off to the other side, swing back, and take a pattern like that. And so it should be a sine curve. So either of these will work for it. And now if you know calculus, and as far as we've gotten on this so far, you know that it's a sine curve, then you should be able to predict the next two graphs yourself, velocity and acceleration. We'll talk about those in a second. So I'm just going to stick with this graph for the following, because this is just the same one but shifted. I mean, it's supposed to be the same size. I'm just, like I said, I'm bad at drawing. So I can say, x equals that. X is a function of t, is that. So, and it's just going to oscillate about that center. So what would it look like if I did a velocity graph? Let's keep this one on there as much as we can. I've got to save a little bit of room because my paper is getting a little bit tight here at the bottom. So velocity versus time. Well, if I look, what's the tangent line here? The slope of this is your velocity, right? So what's the slope here? If I drew this, well, you could tell that the slope here was 0 because it's at the maximum, right? So the slope must be 0. And then your slope here must be maximum. So let's bring that spot down. Let's bring all these spots down because these are the ones I want to talk about. So, but here your slope is maximum but negative, right? So it's going to be here. And here, once again, your slope is 0. Here your slope is maximum but positive. Here your slope is 0. And here your slope is maximum but negative. So once again, if I connect my dots with adding a little bit of curvature for flare. Ooh, yeah. What graph is that? Well, this velocity graph, to me, at least, looks like minus sine, right? And I'm going to throw in a little bit more flare out here. We'll just say V naught. So in this amplitude, I could say this is X naught cosine, the initial position, right, of omega t. Down here, let's say this is V naught sine omega t. So don't forget that minus out front. It's kind of separate a little bit. Well, so what should your acceleration graph look like now? I mean, if you were paying attention earlier to the definition, you should know that it's just going to be the negative of this one, but maybe scaled a little bit differently because, well, we know it's proportional, right? We said earlier that acceleration is proportional to negative x. So we should get a minus cosine graph, whatever we do. But let's go ahead and try it and see if using the slope method we do, because we know that acceleration is the slope of velocity, right? Let's consider these same points again. So I'm going to bring this one down, bring this one down, bring this one down. It's going to be acceleration first time. Well, here my acceleration is maximum, right? Because it's negative because it's sloping the most here. So I'm going to put a point here. And then here, my acceleration, which is the slope of my velocity graph, is 0 because that's the minimum here, so it's not getting any lower. And so here, maximum but positive. Here's going to be 0 because that's the maximum point, so it's not getting any higher. Here it's going to be maximum but negative. And here it's going to be 0. So I'm going to get a graph that looks kind of like minus cosine, but once again, drawn a little poorly. But it's okay if you're bad at drawing. No one will judge you here. Bad drawers anonymous. All right, so those are what your velocity, position, acceleration graph should look like. And we can say this one will look like acceleration will be acceleration initial times, well, minus sine cosine omega t, right? Now if we had done it using this one on the right, this one would have gotten us, because we started with a sine, it would have gotten us a cosine, because here slope will be maximum, right? So it's going to start us at 1, or whatever our amplitude is. And then for our acceleration graph, it's just going to be the sine, but negative. Okay, so your position and velocity graphs and accelerations should all be sinusoids of some sort. If I want to be real technical with these, I can get a little bit more specific in connecting these. You might need to know a little calculus for this to know where this comes from, but I'm just going to write down the formulas, and if you know the calculus, you'll probably see it on your own. So if we say that x equals a sine omega t, and sometimes I'll do like a plus delta or some constant in here just so you can shift it. then my velocity is going to be a omega sine omega t. And my acceleration is going to be minus a omega squared. Oop, this is supposed to be cosine up here, my bad. Cosine. I was looking at the wrong graph. And this should be sine omega t. So what I can do, I can look at this and say, hey, aren't those like the same thing? So acceleration is going to be minus because I can factor out the position from here. So I can say omega squared x, right? Because this a sine omega t is x. All right, so I think I'm going to call it in this video, and I'll see you next one.